So we were discussing about the order of the reaction, rate low, rate constant and all. Now the focus is what are the factors which influence the rate of the reaction? As we know, the factors which influence the rate of the reactions are nature of the reactants, concentration of the reactant. Nature of the reactants we have discussed at some point of time, resting of iron, speed of the reaction, all those things. Concentration of the reaction, with respect to that only we have discussed about the order of the reaction. And the third point is temperature of the reaction condition. So it's an experimental fact that the reaction rate K increases with the temperature. As per our daily life observations, everyday life tells us that the rate of the chemical reaction increases with increase in temperature. Familiar fuels such as gas, oil and coal are relatively inert at room temperature, but they burn rapidly at an elevated temperature. Many food last almost indefinitely when stored in the freezer, but spoil quickly at the room temperature. One of the chemical reaction which we came across in our lab is metallic magnesium is inert in cold water, whereas it reacts with hot water. As a rule of thumb, we can say that the reaction rates tend to double when the temperature is increased by 10 degrees Celsius. To understand why the reaction depends on the temperature, we need a picture of how the reaction takes place. There are two important theories which explain how the rate depends on the temperature. First theory is transition theory, transition state theory, and the other one is collision theory. So if you look at the transition state theory, we know that a bimolecular reaction occurs when two properly oriented reactant molecules come together in a sufficiently energetic collision. Why they require to collide? So of course, if two reactants need to get converted to a product, they must collide. And collision is okay because they have to keep in touch in order to get a product. But they must collide with a sufficient amount of energy. What is the logic behind this sufficient amount of energy? Let us consider a simple reaction. For example, A plus BC gives AB plus C, a simple reaction. The reaction of an atom A with a diatomic molecule BC to give a diatomic molecule AB and an atom C. This is what the reaction. You can have an example from the atmospheric chemistry, that is O plus HCl. Both are gases, react to give OH and Cl, both are gases. If the reaction occurs in single step, if it is an elementary reaction, you have to understand that the electron distribution about the three nuclei must change in the course of the collision such that a new bond, that is AB, develops. At the same time, the old bond BC breaks. Between the reactants and the product stage, the nuclei pass through a configuration in which all three atoms are weakly linked together. We can picture the progress of the reaction like this. So before getting the product, what is going to happen is A will be linked with B and that will be linked with C. If A and BC have filled shells of electron, that means non-paired electrons or vacant low energy orbitals. They are in the most stable state. When they are in the most stable state, once these two molecules are coming closer beyond a particular closeness, they will repel each other. In order to achieve the configuration, that is A dash B dash C, the atom require energy to overcome this repulsion. So the energy comes from the kinetic energy of the colliding particle and is converted to the potential energy in this configuration, that is ABC. In fact, ABC has more potential energy than either the reactants or the products. Thus, there is a potential energy barrier that must be surmounted before getting the reactants can be converted to the products, as depicted by the graphical representation. So according to transition state theory, an unobserved activated complex is proposed to exist as a transition state between the reactants and the products. The activated complex is short-lived because it is highly reactive, may break apart to form the product or revert back to the reactants. And you can have a reaction profile like this. See here, as the reaction progresses, kinetic energy of the reactants is first converted into the potential energy of the transition state. This is the transition state, and is then transformed into the kinetic energy of the products. So this is the transition state. The total energy is conserved at each point along the profile, means the conversion of kinetic energy into potential energy happens, but the total energy is conserved. Please understand, this profile is drawn for an exothermic reaction, so that the delta E for the reaction is for the energy of the reaction, that is the enthalpy of the reaction, is negative. So this position represents reactants and this position represents product, and this represents the transition state. So in order to convert a reactant to product, every reactant molecule need to surmount this energy barrier. This height of the barrier is called activation energy. Actually, activation energy is the property of collision theory, and the configuration of the atom at the maximum in the potential energy profile is called transition state. So you may ask, what is transition state? Transition state is the configuration of the atom at maximum in the potential energy profile, or it could be called activated complex. Since the energy is conserved in the collision, all the energy needed to climb the potential energy hill, that is the potential energy barrier, must come from the kinetic energy of the colliding molecules. If the collision energy is less than the activation energy, the reactant molecules cannot surmount the energy barrier, and simply they bounce it apart. If the collision energy is at least as great as activation energy, however, the reactant can climb over the barrier and converted into the product. One of the experimental evidence for the notion of the activation energy barrier comes from the comparison of collision rates and the reaction rates. Collision rates and the reaction rates. And the Collision rates in gases can be calculated from the kinetic molecular theory, which you have learned in the gaseous states of matter. For a gas at room temperature, that is 298 Kelvin and 1 atmosphere, each molecule undergoes an approximately 10 raised to 9 collision per second, or 1 collision in every 10 raised to minus 9 second. So how long it will take? 10 raised to minus 9 second. Thus, if every collision resulted in reaction, every gas phase reaction means, as per the kinetic energy of the gases, whatever be the number of collision it is supposed to happen, if all those collisions, if it is getting converted to the products, you can expect every gas phase reaction would be completed within 10 raised to minus 9 second. Is it happening? All gaseous reactions are happening within 10 raised to minus 9 second. Then it would have been, we don't have to learn about the kinetics. It doesn't be a matter of area of study at all. By contrast, observed reaction often have half-lives of minutes or hours or days or years. So only, the moral of the story is, only a tiny reaction of the collision, only a tiny fraction of the collision lead to the reaction. So we are discussing about what makes the temperature, every 10 degrees Celsius increase in the temperature will double the rate of the reaction. What makes that to happen? So let us see that. So the enthalpy change for the reaction is the difference in the activation energies of the forward and the reverse reaction. So as you know from thermodynamics, this is an exothermic reaction. You can plot a graph for endothermic reaction. So then the enthalpy will be positive. So please understand, the enthalpy change for the reaction is the difference in the activation energies of the forward and reverse reaction. So this is what the transition state theory means. There is a transition state is formed. So this transition state will have more energy than that of the reactants and products. So every reactant, if it has to get converted to the product, there will be the formation of a transition state. That is the contribution from transition state theory. So we'll look into the collision theory. Actually, in order to produce the transition activated complex, collision should happen. But as far as the transition state theory is concerned, there is only the point is, there is the formation of a transition state which has more energy than that of the reactants and the products. And you will get a clear picture when you learn about the collision theory. As per the collision theory, in order for two molecules to react, all the chemical bonds have to be broken. That requires energy. I have already told you. Collision theory considers that such energy is provided by the kinetic energies of the molecule upon their collisions. The collision theory can qualitatively explain this collision theory. When you look at the energy profile diagram, that could explain why the reaction rate K increases with the increase in temperature, and why only 1 out of the 10 raised to 10 collision results in the reaction. That's what just now I told. So collision theory considers the distribution of the kinetic energies of the molecules. Activated complex theory only says the energy profile diagram. So as per the the energy profile diagram that we have drawn, that react and converted to product, it is the contribution of transition state theory. Now the collision theory considers the distribution of kinetic energies of the molecules. So if you look at this, you could see that this temperature, the T1 temperature, is lower temperature, This is higher temperature. The total area under the curve is unity. So if you take this one and this one, the total area under the curve, you could see that it is unity. And EA, this arrow mark represents EA. So EA we have already discussed. It is the minimum energy possessed by the molecule in order to convert from reactant side to the product side. So if you look at this, if the minimum energy required for the reaction to occur, that is the activation energy, is indicated by the arrow in the accompanying figure, then the fraction of the molecule possessing this energy will be greater at T2 than at T1. So this is the higher temperature and this is the lower temperature, and this is the kinetic energy of the molecule, and this point represent, as I have told, the activation energy. So in order to convert the reactants to the product, the reactant molecule to the product molecule, they have to possess the minimum energy. That's what we call activation energy. So you could see that after the activation energy, the area, this area to the right of EA is the fraction of the collision with an energy greater than or equal to EA. So those molecules will get converted to the products. So you please keep in mind, there is an equation that representing the fraction of the molecule which possess the kinetic energy, that is F is equal to E raised to minus EA by RT, where the R is the gas constant, that is 8.314 joules per Kelvin per mole, and T is the absolute temperature in Kelvin. Note that the fraction, that is F, is very small number. So we'll come back to the point. So what here we have to understand is, what makes an increase in 10 degrees Celsius of the temperature will make the reaction rate to be doubled. If you ask, that could be well understood from this graph, that the fraction of the collision that are sufficiently energetic to result in reaction increases exponentially with increasing temperature. So here if you look at this part, that is at lower temperature, whereas when it is higher temperature, the area is getting almost doubled. When the area is getting almost doubled, that means the fraction of the molecules which possess the activation energy is getting doubled, so that the rate of the reaction is also getting doubled. So collision theory could explain well how an increase in temperature will increase the rate of the reaction. So here let us consider certain interesting facts. So regardless of T, the fraction of the molecule possessing enough energy will be small, and thus the rate of the reaction will be much less than the collision frequency. So the second point that is we have to remember collision theory could explain is why all the collisions are not leading to the product. That could be explained by the second sentence. So the equation is F is equal to E raised to minus EA by RT. Let's consider a reaction having an activation energy that is 75 kilojoules per mole. The value of F at 298 Kelvin is 7 into 10 raised to minus 14. How can you get it? So F is equal to exponential 75,000 joules per mole divided by 8.314 joules divided by Kelvin per mole into 298 Kelvin. This gives, if you simplify it, you can get it as E raised to minus 30.3, that is equal to 7 into 10 raised to minus 14. That means only 7 collision in 100 trillion are sufficiently energetic to convert reactants to the product. As the temperature increases, the distribution of the collision energies broadens. Here you could see that as the temperature increases, the curve is becoming broadened. So the distribution of collision energies broadens and shift to the higher energies, resulting in a rapid increase in the fraction of collision that leads to the products. At 308 Kelvin, we were looking at 298 Kelvin. At 308 Kelvin, if you take, for example, the calculated value of F for the reaction with the EA is equal to 75 kilojoules per mole is 2 into 10 raised to minus 13. Before it is 7 into 10 raised to minus 14. Thus, the temperature increase of just 3% from 298 Kelvin to 308 Kelvin increases the value of F by a factor of 3. So collision theory therefore accounts nicely for the exponential dependence of the reaction rates on reciprocal temperature. As T increases, that is 1 by T decreases, F is equal to e raised to minus EA by RT increases exponentially. So collision theory also explains why the reaction rates are so much lower than the collision rates. Collision rates also increase with increase in temperature, but only by a small amount, that is less than 2% on going from 298 Kelvin to 308 Kelvin. So as a thumb rule, we can say that every 10 degrees Celsius, for every 10 degrees Celsius rise in temperature, there will be twice the rate of the reaction will get increased. But as the temperature goes beyond 308 Kelvin, it decreases slightly. So one factor that decreases differentiate the rate of the reaction from the collision rate is the fraction of the molecule that possesses the activation energy of the reaction. Even if the reactant collide with sufficient energy, they won't react unless the orientation of the reaction partner is correct for the formation of the transition state. For example, a collision of A with the C end of the molecule of BC can't result in the formation of AB. Before we were discussing about A plus CB gives AB plus C. So in order to produce AB, A has to collide with B. If it is colliding with C, it will not lead to the formation of the product. So this is what we call orientation factor. So the reactant molecule would simply collide and then separate without the reaction. So the fraction of the collision having proper orientation for the conversion of the reactants to the product is called steric factor. It could be represented by rho or P, small letter P. For the reaction A plus BC gives AB plus C. You have already said. The value of P is expected to be about 0.5 because A has a nearly 1:1 probability of colliding with each other of the B and C. So if A is going to collide with BC or CB, A can either collide with C or A can either collide with B. So the possibility is 1:1. So the probability is 1:1 provided B has similar B and C is having similar size and the electronic properties. Suppose in reactions of larger, more complex molecules, rho is considerably less than 0.5. So what comes to the picture is the orientation factor. Suppose if I am taking a session for you students, suppose if you people are sitting not facing towards me on the opposite direction, will my class be effective? No. You have to, I have to stand in front of you, you have to sit in front of me, then only the orientation will make the effectiveness of the class. So now let's see how the two parameters, that is, we have already discussed the two parameters, one is f, the other one is p, enter into the rate law after few minutes. So collision theory is stressing one more point, that is the importance of the orientation of the molecule. Rate of the reaction is also be limited by the orientation of the molecules at the time of their collision. I have taken an example, that is N2O plus NO gives N2 plus NO2. So here the collision, this is favorable collision, these two are unfavorable collision. And let us see what is the difference between the collision and transition. Transition state theory states that there is the formation of a transition state during the course of the reaction. The transition state is supposed to have more energy than the reactants and the products. Every reactant has to surmount, has to go through the transition state, then only it will get converted to products. Collision theory states that the transition state is having more energy than that of the reactants and product. In order to achieve that energy barrier, or that is the energy of the transition state, they have to collide each other with a sufficient amount of energy. That sufficient amount of energy is what we call activation energy. So these two are very similar. Using slightly different considerations, both theories could explain why K depends on T and why K may be very low. Both can be used to get very important formula for the dependence of the K and T. So both could be used means I would like you to recall two equations. One is two parameters. One is the fraction of the molecule which process activation energy, that is e raised to EA by RT. The second one is the orientation factor. Now let's get into an interesting point. Now let us see how quantitatively how the two parameters, that is the orientation factor and the fraction of molecules which possess the minimum amount of energy, that is the activation energy, enter into the rate law. Since bimolecular collisions between any two molecules, say A and B, if you take A and B, occur at a rate that is proportional to their concentration, we can write collision rate is equal to Z into A into B. Just like we write the rate equation, here I have written Z is called, so it is reaction rate is K into A into B, but here the collision rate is Z into A into B. So Z is called a constant collision frequency and has the unit of a second order rate constant, because two collision substances are there. The reaction rate is lower than the collision rate. So we wanted to know about we have to compare the reaction rate with the collision rate. So the reaction rate is lower than the collision rate by a factor of orientation factor P and F, because only a fraction of the colliding molecule have the correct orientation and the minimum energy needed for the reaction. So you can write reaction rate is equal to P into F into collision rate. That is P into F into Z into molar concentration of A into molar concentration of B. So we already know that the reaction rate from the previous studies, reaction rate is equal to K into molar concentration of A into molar concentration of B. So now you can write K is equal to P into F into Z. So This equation is what we call Arrhenius equation. So Arrhenius equation could be written as, if you elaborate what is F, K is equal to P into Z into e raised to minus EA by RT. So what is K? K is the rate constant. What is P? That is the fraction of collisions with proper orientation for the reaction. Fraction of collisions with proper orientation for the reaction. And Z, what is this Z? Z is called collision frequency, or it could be a constant related to the collision frequency. Now this part, e raised to minus EA by RT, is called the single S, okay, fraction of collisions with sufficient energy for the reaction. Means fraction of collisions with activation energy. T is as usual temperature, R is the gaseous constant.
Arrhenius constant A
expression
is equal to P into Z.
is what we call Arrhenius equation, named after Svante Arrhenius, the Swedish chemist who proposed it in 1889 on the basis of experimental studies of the reaction rates. Effect of temperature on the reaction rate could be quantitatively explained by Arrhenius equation. Experimental observation says that the rate of the reaction generally increase with the temperature roughly doubles. Arrhenius expression illustrate this for the rate constant. K is equal to A into, or taking the logarithm, you can write ln K is equal to EA by RT plus ln A. EA is the activation energy in joules per mole and A is the frequency or pre-exponential factor. What is the meaning of A and EA? A is the frequency of collisions or pre-exponential factor. The factor related to the collision frequency of a molecule represents the limit to how fast two molecules can react. Molecules cannot react unless they have enough energy. EA is the activation energy. Even when the molecule collide, they cannot react unless they possess enough energy. EA is the minimum energy that the reactant must possess in order to react. So how do you find out the activation energy? So if you take this equation, as we have discussed before, you can plot the equation of straight line. Y is equal to mx plus c, and the 1 by t will be the x, and ln k could be taken as y, and c is the intercept, m is the slope. So m is the slope means minus EA by R will be the slope. So you can plot a graph like this, and if you plot a graph like this and if you find out the slope, at the slope you have to divide by R and you will get the activation energy. This is from the graphical method. So temperature effects, one more extension for the Arrhenius equation. You can have two different rate constant for a particular reaction at two different temperatures, so that you will have an equation like this: ln K2 by K1 is equal to EA by R into 1 by T1 minus 1 by T2. Arrhenius equation can relate the rate constant at two temperature. In the equation, temperature in Kelvin and R is in standard SI unit. It allows finding EA by measuring K at two different temperature. This is a numerical way of finding out the EA value. Or it allows finding K for any temperature if EA is known and K for one specific temperature is unknown.